Hello everyone, and welcome to the Undergraduate's Guide to Semiconductors. Now this will be an introduction to semiconductors covering the basic physics, the p-n junctions that make up these semiconductors, and the different cases these p-n junctions face, along with the band gap that makes these p-n junctions work. Now there are two types of semiconductors. There are intrinsic semiconductors, which are pretty much just like basic silicon, and we just manufactured it into a wafer, and by its physical properties it is a semiconductor. But an extrinsic semiconductor is an intrinsic semiconductor that we've tampered with or doped. Now, how we dope these is shown in this diagram here. Let's say this rectangle is a sheet of silicon, and on this side we put trace elements that have one less electron than silicon, and on this side we put trace elements that have one more electron than silicon. Now, this something kind of interesting happens here because we know that the electron is going to want to jump the gap and fill in this hole because this hole is relatively positive and this electron is negative, so it's going to want to fill in there. But since we're in a defined section already, that hole is going to move over to this side because an electron's gone, and that hole just perpetuates over to this side. And in an ideal world, this hole will want to reach this end of the material, and this electron will want to reach this end of the material. But in reality, that really doesn't happen because that electron that jumps requires energy. And we found that in real life, it usually stops by this dotted line, and it kind of hangs out here a little stuck in the P region. And inversely, the hole is stuck over here in the N region, and it's kind of like this traffic jam. No one's going anywhere, and there's nothing to act on it from the outside, so it's kind of stagnant, and this is called the depletion region. Now, this depletion region has positive charges on one side and negative charges on the other, so from physics, we know that there is an induced E field because of this. And that also means that if we put our voltage probes here and here, we'll find that there's a voltage across this even though there's no battery or any other type of power element here, which is very intriguing and was capitalized upon. Several Silicon Valley engineers found that you can do different, there are many different applications to this phenomenon. Now, there are three different biases or cases when it comes to these p-n junctions. The first one is no bias that we saw before, and it's the traffic jam. Nothing's happening, nothing's acting on it, and so it's going to stay like this for a very long time. Now, the second one is called forward bias. Now, forward bias is where you attach a voltage source or a battery to it, and this is where I'd like to remind us about the semantics with electronics. Current is defined as the electron moving and not the hole moving. So the electron that was stuck here will move through this wire from plus to minus and back into its original side. And inversely, the hole will move through the wire from minus to plus back into its original side. So there's no traffic here at all. Everything's just nicely flowing, and there's no traffic at all. And the last bias is called reverse bias. And this essentially makes things a whole lot worse because you flip the voltage source, and now you have electrons going into the hole region and getting piled up in the middle here, and you have holes going into the electron region and getting piled up in the depletion region area. And it's essentially a worse traffic jam. Nothing's happening. All you're doing is making this E field stronger, and you have a defined voltage. Now, later on, if you're taking a microelectronics course or some type of semiconductor course, you'll see that this reverse bias leads into something called a Zener diode, which is a very practical application for what's at first seems like a useless bias in general. Now, I keep saying band gap, but what exactly do I mean by band gap? Well, the bands are separated into two different bands. There's the valence band and the conduction band. Now, if this is an electron, and it has to cross this gap. I usually like to think of this like a river, and you want to cross the river by jumping it. You really don't want to fall in here, or else you'll probably get washed back ashore. Now, in no bias, nothing's happening, but in forward bias, there's kind of a tailwind of sort that will push you in midair and help you jump the gap. And if you're in reverse bias, there's kind of a headwind that the second you jump, it'll just push you right back to shore and you're not crossing at all. So I'd like the viewer to take from this video of how exactly a p-n junction is made and how each three of these biases are different in their own way. This is pretty much the default. This is a short and this is an open. And I will see you guys next video where we cover equations dealing with these p-n junctions and semiconductor physics in general. Thank you.